One of the simplest connections we can have with the periodic table and electrons and electron configurations is trying to turn specific electron configurations into a more general form. So these are some examples for our alkali metals. For example, we know that they are going to have one valence electron. We can represent that more generally by saying that they have an s electron, one of them, and then n represents which row is that in, or which period. N specifically refers to what principal energy level is it in. But here we can just think of it as what number. If I were to go down to group 12, and remember we're numbering across 1 through 12, group 12 is where we're talking about zinc and cadmium and mercury. They have filled the S sublevel, but they also have that filled D sublevel. So these elements right here, my zincs and my cadmiums, I've got NS with 2, I've got D with 10, and then I can even be a little bit more specific to point out that the D that I am talking about is one less than the row that I'm in. When I get over to the halogens, so fluorine and friends, and to the noble gases, I have this general electron configuration. It is important to remember how like helium does not fill the p sublevel. So if, depending what you're asked in terms of how to write general ones, it is good to note that yes, we call it an octet rule. Yes, we're thinking about 8 electrons, but really the octet rule, or the set of 8 electrons we're talking about for a filled energy level, is just to say that however many levels and sublevels are there are likely to be filled. The other thing to point out, once we get down into row 4 and below, we would have D, and those would all be filled. And if we're in row 6 or 7, we would also have 14 Fs as well. To take this to the next step and think about magnetism, we're looking for any or all atoms that have unpaired electrons. To recognize unpaired electrons, we have to look beyond just the electron configuration to the orbital diagram. Group 1, in that they have that one box or one line, always with a single arrow. So they're always going to have just one unpaired electron in their atomic state. Those elements tend to be very reactive and unstable as atoms, so we don't experience those as magnetic, but in their atomic state, they are. Group 7, and group 7's back behind me, moved the wrong way. That's manganese, technetium, rhenium. They have 5 unpaired D electrons. So not only do they have some that are unpaired, they have kind of the maximum amount that's unpaired. They've filled their 4 or 5 or 6s, and then their D, it's 1, 1, 1, 1, 1. So those tend to be have the ability, to be very magnetic. Once again, we're talking about paramagnetism. Unpaired electrons make something paramagnetic, whereas if everything's paired, we call that diamagnetic because the magnetism dies. But lots of transition metals have the ability to be magnetic. Iron doesn't have 5 that are unpaired. It has 4 that are unpaired, but that's still enough for iron to be one of the things that we think of as most magnetic. When we get down here to group 15, that would be the nitrogen family, sometimes called the pictogens. In their atomic state, they would have unpaired electrons. A lot of times nitrogen is diatomic and phosphorus isn't individual atoms. So in maybe the state we would find them in nature, we might not see that magnetism, but in an atomic state, we're looking just for unpaired electrons. And as it says, there's other nonmetals that are unpaired, and especially as you start bonding them and going into bonding theory beyond this course, you would be able to see and describe that even more. Right here is coming back to something we did before, electron configurations related to ions. So when it asks what could only form a +2 ion, we would think about what is something that kind of maximizes attractions, minimizes repulsions, or more simply, becomes more stable by only losing 2 electrons. Because zinc, cadmium, and mercury have filled their D sublevels, and in mercury's case, even its F sublevel, it's likely to lose the S electrons without losing any more. That does not necessarily make them more stable or minimize repulsions while maximizing the attractions. Some things that could form +3 would likely be scandium and yttrium, and then even going down to lanthanum and actinium. They have their S sublevels with 2 electrons. Those are the valence, but they also have just 1 electron in the D sublevel. It's fairly weakly held compared to others in terms of the attraction from the nucleus. It would be less than many others. So it is possible and common that they would form the +3. We already looked at an example with iron, but the emphasis here is that these properties are not unique to single atoms, but they belong to everything in the family or everything with a similar electron configuration. So if iron can do it, then ruthenium, osmium, and hassium likely will be able to do the same thing. We're eliminating the pairing and we're minimizing the repulsion. But I want to restate again, it is not our responsibility to memorize every ionic charge and every possibility. What we should be able to do is explain when we are told that something forms a +2 but no other ions, or when something could form a +2 and a +3, why it forms that way. Manganese, I can't quite find it with my finger. There it is actually something that is very common to form an oxidation state of +7 in polyatomic ions. And +7 seems like a really extreme number until we recognize that manganese has 2 S electrons and 5 D electrons. It doesn't necessarily form a full +7 ion very commonly, but sometimes in the compounds, we'll see that that oxidation number, which we may have seen before, but we'll also be coming back to, makes sense based upon its electron configuration.